So section 6.4, what we need to know here, the key idea, I'll just start with that. I'll just start with what the absolute key idea for this is right here. This rule is really the short and skinny of what we're talking about today. Okay? The short and skinny of what we're talking about today. Where if I have the nth root of a, so if I have the nth root of a, that can be rewritten as a to the 1/nth power. Okay? That is the short and skinny of it. Let's go ahead and take a look at a quick example of that right above that. So if I have the square root of 36, I can rewrite that as 36 to the 1/2 power. Notice the index of a square root is 2, and notice that the index goes into the denominator of the fraction exponent. Okay? So 36 to the 1/2 power. If I have the cubic root of 64, again, that's going to be 64 to the 1/3 power. The index is the denominator of the fraction. Fourth root of 16, again, it's 16 to the 1/4 power. The index is the denominator of the fraction. So, why is this? Why can we do this? Well, if we look up at the very top sentence here, this sentence right here, they're trying to show us how that comes about. Okay, they're trying to show us how that comes about. So, let me kind of explain it to you here. Let me show you step by step. So if we have a to the x power, and that equals the 4th root of a cubed. Okay? A to the x power is the 4th root of a cubed. So we are basically saying that if we take a to the x times a to the x times a to the x times a to the x, so a to the x 4 times, we're going to get a to the 3rd power. Okay? That's what they're saying. The 4th root of a to the 3rd power is a to the x. That's what they're telling us. Now, if I multiply a to the x's together, if we look at our rules of exponents, if we have the same base, we add the exponents. So basically, I'm going to have a to the x plus x plus x plus x power, which is 4x. Okay? So a to the 4x power equals a to the 3rd power. Now, at this stage, I'm hoping everybody then sees that 4x must equal 3. If you don't see that right away, consider this. 5 to the x power equals 5 squared. Doesn't x have to equal 2? If 5 to the x power is equal to 5 squared, right? Doesn't x have to equal 2? Doesn't that just make sense then? Right? Well, that's all the logic I'm using here, that if a to the 4x power equals a to the 3rd power, then 4x must equal 3, right? You guys agreeing with that logic? Okay. Well, then I can finish this by dividing both sides by 4. And that means x equals 3/4. So, let's take a look at what that means for us. Back to the original problem. If I have a to the x power, but I know x is 3/4, that means a to the 3/4 power is equal to the 4th root of a to the 3rd power. Okay, that's what I just showed you here. So again, like I said at the very beginning, the index ends up being the denominator of the fraction. Now, notice what happened to the numerator. The numerator of that fraction was a 3. Where did that 3 show up? It was an exponent. Okay? So if you have a rational exponent simply means you have a fraction for an exponent, okay? If you have a fraction for an exponent, the numerator is an exponent. It still means squared or cubed or to the fourth power. The denominator is the index of a root. That means square root, cubic root, fourth root, fifth root, so on and so forth. Okay? So the numerator is still an exponent. The denominator is a root. All right, well, let's then think about this for a second. Let me show you why would we want to do this. Why would we want to write radicals as rational exponents? Boy, that sounds confusing. Why would I ever want to do that? Well, let's take an example of it. What if I go back to some old problems we had worked, and what if I say I want the cubic root of 5 times the square root of 5. Cubic root of 5 times the square root of 5. Now, from the ideas or the knowledge that we have from our first 3 sections of this unit, are we able to multiply these? No, a lot of you are shaking your head, and that is excellent. That's exactly the answer I expect right now. No, we are not able to multiply these because we learned a rule that said the nth root of a times the nth root of b gives me the nth root of a times b, right? They have to have the same index in order to multiply the radicands. I 100% agree with you when it's written in radical form. The whole point of what we're doing today is that we can write it in exponential form. Meaning, I can rewrite the cubic root of 5 as 5 to the 1/3 power. And I can rewrite the square root of 5 as 5 to the 1/2 power. That now allows me to use my rules of exponents, which says that if I have a to the m power times a to the n power, I have a to the m plus n power. So if I have the same base, I can just add the exponents. Right? So, looking at this, we need to add our exponents. So I'm going to have 5 to the 1/3 plus 1/2 power. So if I'm adding 1/3 and 1/2, anytime I'm adding fractions or subtracting fractions for that matter, what do I need to have? A common denominator. So what would my common denominator be here for 3 and 2? 6. So that means I have to multiply the top and bottom of my first fraction by 2.
5, 6.
And I have to multiply the top and bottom of my second fraction by 3, so that I have 5 to the 2/6 power plus 3/6 power. Now I can add those fractions. And so now I get 5 to the 5/6 power. If I was to rewrite this in radical notation, this would be the 6th root of 5 to the 5th power. This is written in exponential form. This is written in radical form, or radical notation. We'll probably call this exponential notation. Both of these mean the exact same thing. It is simply a different way of writing it. And of course, if we left it in radical notation from the beginning, we wouldn't be able to work with it. There's no rules for us to be able to work with it in radical notation. But if we change it to exponential notation, now we can actually do something with it. Now we can work with it. So that's the point. That's the why do we do this. Because now we're able to work with more numbers in more situations. Okay, so in our notes here we have a key concept for rational exponents. Right here is our key idea. If we have a to the m over n power, so it's a rational exponent. Rational exponent means a fraction exponent. So we have a to the m over n power. Please remember that the m is the exponent. The n is the index. Okay? So the denominator of the fraction is always the index for our root. So then there's two ways of writing it. We could say we have the nth root of a to the m power, or we could say we have the nth root of a all raised to the mth power. Okay, so that right there gives us our rule. That is kind of the meat and potatoes of this section. And let me show you, why can we write that two different ways? Why are there two different forms for where we can write this? Well, if we go over to the side here again, if I have the cubic root of x squared, okay, the cubic root of x squared, I can rewrite this. I can rewrite this using rational exponents. I have something raised to the 1/3 power, right? Because I have a cubic root. And so the index becomes the denominator of the fraction for my exponent, right? So I have then something to the 1/3 power. Well, what is that something? That something is x squared. Okay? Now, looking at this, if I have a power raised to a power, what do I do with that? Do you remember the rule? It's over on the board there. What do I do if I have a power raised to a power? I multiply the powers, right? I multiply the powers. Well, is multiplication commutative? Remember that vocab word from way, way back? 7th grade, possibly, if not before. Commutative property of multiplication means it can be switched around. It means 5 times 2 is the same thing as 2 times 5. Okay? So multiplication is commutative, so therefore, yes, I can switch this around. Meaning I could write this as x to the 1/3 power raised to the 2nd power. Why? Because it doesn't matter if I take 1/3 times 2 or if I take 2 times 1/3. I get the same answer. Right? Well, then if I rewrite that in radical notation, I now have something raised to the 2nd power, and that something is the cubic root of x. So this means the exact same thing as this. There is no difference. The only difference is the notation, and therefore the difference might be, how do you want to work it? What is the easier method? Okay? For example, what if I gave you 9 raised to the 3/2 power? 9 raised to the 3/2 power, I could write that two different ways. I could say that I have the square root of 9 raised to the 3rd power, or I could say that I have the square root of 9 to the 3rd power. Mathematically speaking, it means the same thing. Notation-wise, it's a little different. Which method do you think would be easier? Method number 1 or method number 2? All right, so in this particular example, option number 1 is easier because we're able to say the square root of 9 is 3, just from knowing that, having that memorized, and then 3 cubed, 3 times 3 times 3, is 27. That is a much simpler way of working this. So, depending on the problem will depend on which way you write it. Okay, but it all depends on the problem. Let's try some examples. So if we look at example A, we have 216 to the 1/3 power. How am I going to calculate that? How do I even know what they're asking me to do?
The 260, like the denominator is the exponent, and then the denominator is the index.
The numerator is the exponent, and the denominator is the index. So since we have a numerator of 1, do we really care about that much? Is that going to do much for us? No. But what about that index? What does the index of 3 tell us we're doing? We're taking a cubic root. So the cubic root of 216. Hey, I believe that's something that's on your chart.
6.
The answer is 6. So 216 to the 1/3 power is 6. Okay? Let's take a look at part B. Part B, I have 7 to the 1/2 power times 7 to the 1/2 power. Use your rules of exponents. Those rules are in your concept bite, which is the second set of notes, second sheet of notes in your notes packet. Or if you want to look ahead to what we're going to be doing, talking about again tomorrow, look at the back of your 6-4 notes. They're rewritten there for you. Okay? On the back of your 6-4 notes, they're also sitting right there. All your rules of exponents. Okay? So we have the exact same base. Our base is 7. So what do we do to the exponents? We add them. If we're multiplying the same base, we add the exponents. Oops, and of course I wrote multiply because I was saying multiply when I was writing. We add the exponents. So what is 1/2 plus 1/2? 1/2 plus 1/2 is 1. 1. If I have half a candy bar and you have half a candy bar, together we have 1 candy bar. So we have 7 to the 1 power, or just 7. And of course the answer is going to be 7. What if I rewrote this in radical notation? I have the square root of 7 times the square root of 7. They have the same index, so I have the square root of 7 times 7, which is the square root of 49, which is 7. Okay? So of course it's going to be the same thing. But we want to be thinking of it in exponential form. We want to get used to working with rational exponents. Example C. Again, we want to be thinking in terms of exponents. Don't try to rewrite this as 4th roots. Okay? Think in terms of exponents. So, can I rewrite 5 using exponents? 5? No, I can't. So it stays 5 to the 1/4 power. But, can I rewrite 125 using exponents? What is it? 5 cubed. So I have 5 cubed raised to the 1/4 power. 5 cubed raised to the 1/4 power. So then, what do I do here, folks? What do I do with powers? Power raised to a power? I multiply them. So I have 5 to the 1/4 power times 5 to the what power? 3/4. 5 to the 1/4 power times 5 to the 3/4 power. Well, now I'm multiplying two numbers that have the same base. What do I do with the exponents? Add them. 1/4 plus 3/4 is 4/4, or 1. All right, let's go through a couple of examples real quick then. So, I'll give you guys 20 seconds. Please rewrite x to the 3/7 power in radical form. Okay, taking a look at the answer then. Remember, the denominator is the index. So I am taking the 7th root of something. And what am I taking the 7th root of? The numerator is the exponent. So x to the third power, I'm taking the 7th root of x to the third power. That is one way of writing it. Or, I could have said, again, the 3 is the exponent, so I could have said that I have something raised to the third power, and again, the 7 is the index, so I have a 7th root of x. Okay, if you're going to write it this way, you have to have it in parentheses. You have to show that in parentheses, that's being raised to the third power. Okay? Let's take a look at the next one. Go right below this. Please rewrite square root of a to the 5th power in exponential form. All right, so going backwards now, we have radical notation. We want exponential notation. Please remember that the index is always the denominator of the fraction. The numerator of the fraction is the exponent. So in this case, we have a to the 5 halves power. The correct answer here is a to the 5 halves power. The exponent is the top. The index is the denominator. Let's try another. Please write this one in exponential form. The 5th root of b to the 3rd power. Okay. We should have b to what power? 3/5 power. b to the 3/5 power is the correct answer here. The denominator is the index. Okay. If we look at the problem right above this, we're not going to have a chance to work this fully in class today. But in this problem, the first thing I want to talk to you about is how to change this into a rational exponent. We don't have decimal exponents. We change them to rational fractions. Okay? So we need to take 3.5 and we got to change that into a fraction. So probably the easiest way to do that is to change 0.5 into a fraction. What is 0.5 as a fraction? 1/2. So this is 3 1/2. Then you use the round the world method is what I call it. You take 2 times 3, which is 6. Then you take 6 plus 1, which is 7, and you keep the denominator. So 7 halves is what 3.5 is as a fraction. So this is y to the negative 7 halves power. Okay? They want us to write that in radical form. We will finish this example tomorrow.